Okay, this is the second part. Zoom crashed for some reason, but let's continue. So we did 7.8 last time. Now we're doing 7.9. Let's go to the whiteboard and let's just rewrite this system. So again, for this system or for these set of problems, you're given A going to R going to S. You're given two reaction rates. R is equal to K1 Ca squared and K1 is 0.4. Rs is K2 Ca and K2 is 2. And I'm given Ca naught is equal to 40 moles per meter cubed. It's going inside a reactor. So for 7.8, it was a CSTR. For this case, it's a PFR, and you basically need to calculate Ca, Cr, and Cs. So last time we said for a CSTR to calculate the output composition. So Cs is equal to phi S over A multiplied by minus delta Ca. Similarly, Cr is equal to phi R over A multiplied by minus delta Ca. Right? I think this is 10. So these are for CSTRs. These are the ways to do it. However, for a PFR, the equation you're going to use is different. So in a PFR, the way to do it is Cs will be minus integral of Ca naught to Ca f of phi S over A dCa. And be careful when doing these integrals because similarly again as well for CR, same thing, minus Ca naught to Ca f of phi R over A dCa. So you have to do some integrals, can be a bit tricky, but let's approach them and let's do them. Okay, let's go back to the problem. I think you're told XA is 0.9. So again, similar to the previous one, you're told that XA is equal to 0.9. Okay, so let's start off by doing the first one. Let's calculate CS first. Okay, so I'm gonna remove this guy right here, and because we need some space to work. So let's calculate the first expression, which is the outlet concentration of a PFR for CS. So I need the instantaneous yield, right? Or instantaneous fractional yield in order to do this. So let's do this. So my instantaneous fractional yield phi of S over A, this will be equal to K2 Ca divided by K1 Ca squared plus K2 Ca. Now integrating this expression with respect to Ca is difficult. I mean, it's not difficult, it's exhausting. You know, it's time consuming, let's put it this way. So if you have a calculator, you have a computer, you're familiar with computational tools to do it, go ahead and do it. Alternatively, you can make your life easier before doing any integration. And the way to deal with these types of fractions is I'm going to flip it first. So I'm going to flip it so I get K1 Ca squared plus K2 Ca divided by K2 Ca. And this can be divided to K1 Ca squared over K2 Ca plus K2 Ca over K2 Ca. This guy right here is 1. And I'm going to cancel one of the Ca's here. So this will be K1 over K2 Ca plus 1. K1 is 0.4. I'm given K2 is 2. So 0.4 divided by 2 is, how much is that? 0.4 divided by 2, this is 0.2, right? So this is equal to basically 0.2 Ca plus 1. So if I flip it back, so therefore phi of S over A, so I flip it, do some simplifications, and then flip it back will be 1 over 0.2 Ca plus 1. You can see this is a nice cute expression. You can integrate it very easily to get what you want. So now if I'm going to integrate it, Cs is equal to minus. I'm going to remove the minus and change my limits. Again, there's another simplification you can do. So this will be integral from Ca f CA note. So I remove this minus and flip these two guys of 1 over 0.2 CA plus 1 dCA. And this integral right here is equal to 1 over 0.2, right? 1 over this multiplied by ln of the denominator, ln of 0.2 CA plus 1. And this will be from CAF, which is 4, to CA note, which is 40. And I calculated CAF because I'm given the conversion, I'm given CA note. Can calculate CAF to be 0.4 directly. If you do this calculation, you're going to get CS to be equal to 8 moles per meter cubed. This is the composition, outlet composition. The main move here, or the main trick, basically is to be able to manipulate this fraction to make the integration easier if you're doing it by hand. Again, if you're using a calculator, you know how to use the graphical calculator to do this for you. Do it. However, it's always good to know these manipulations as well. Okay, now let's do the same thing for CR. Okay. So okay, this will be 11, right? So I'm doing the same thing for CR. This will be, or first thing I need to get is the phi of R over A, right? So phi R over A, this will be K1 CA squared divided by K2 CA plus K1 CA squared. I'm going to do the same manipulation. I'm going to flip it. 1 over phi of R over A. This will be K2 CA plus K1 CA squared. And take note of the different ways of doing this, right? For CS, I only had the CA at the top. For this guy, I have CA squared. Two different methods, know them, and they're going to show up. K2CA plus K1CA squared divided by K1CA squared. If I split this fraction, or if I, I'm going to get K2 for K1 multiplied by 1 over CA plus 1, right? And then if I, and this basically will be equal to it. So if I consolidate them back again, I'm going to get 5 plus CA over CA. So I basically, so K2 is 2, K1 is 0.4, so K2 over K1 is 5. And I just consolidated this fraction, so I get 5 plus CA over CA. So now if I flip it back, I'm going to get phi of R over S is equal to CA over 5 plus CA. And this expression is a lot simpler than this expression, so it will make your integration somewhat easier. So let's do the integration. So now I want to calculate CR. And again, I'm going to remove this negative and flip these two guys. So I'm going to get CAF to CA note of CA over 5 plus CA dCA. And in order to do this easily without having to do any type of splitting a fraction or anything like that, I'm going to CAF to CA. I'm going to CA plus 5 minus 5 divided by 5 plus CA dCA. So I just added 5 and subtracted 5. I just, plus 5 minus 5, and then I'm going to split this fraction. So I'm going to get integral CAF to CA of CA plus 5 divided by CA plus 5 minus 5 over CA plus 5 dCA. This is 1. So this reduces to becoming an integral CAF to CA of 1 minus 5 over CA plus 5 CA. And then if I integrate this expression, I'm going to get, this will be basically CA minus 5 ln of 5 plus CA, and I'm plugging in numbers from CAF to CA, so from 4 to 40. You do this calculation, you should get CR to be equal to 27.95 moles per meter cubed. Learn the mathematical manipulations, know how to do it. This is going to show up, and now you have C. You have all the concentrations. You know it's a PFR. You can calculate tau. If you don't know how to do it, go to office hours or look at the previous slides. Okay, let's clear everything. Let me go back to the homework. 710, find the operating condition which maximizing CS in a mixed flow reactor. And then I have 711, which is saying find the operating condition which maximizes CR in a mixed flow reactor. Okay, so now I'm looking for maximums, right? When you need to find maximums, always remember that unless you have a given equation, like we had in chapter 8, or we also have in chapter 7, we have some equations, you might need to do some derivation, right? You might need to get a derivative of a function to determine its maximum. Okay, let me go back to the whiteboard. Zoom is crashing too much. One second. Find the operating condition which maximizing CS in a mixed flow reactor. Right. Let me make sure I'm sharing. Okay. So this is page 12 maybe. This is 710. I want to maximize CS in a CSTR, right? So let's look at the function of a CS in a CSTR. We said CS is equal to phi S over A multiplied by minus delta CA. We already did this previously. And the equation we were using was 1 over 0.2 CA plus 1 multiplied by CA naught minus CA, right? Okay. Looking at this just before doing anything. So technically to get the maximum, it's the point where I have DCS by DCA is equal to 0, right? This is my maximum point. DCS by DCA is equal to 0. However, this is a special case. Just know that it's a special case. On a test or something, you're not going to get something like this. Because this function is written this way, mathematically, this looks something like this. So I don't have a maximum. It diverges, diverges at different points. So if you do the integral, you're gonna get a function which you're gonna get 0 equals to 0 or something like this. So if you do the derivative, you can do it and try it. But for now, I'm telling you, even if you get to the situation where you do the derivative and you can't get a maximum, or the function does not have a maximum, we need to try a different approach, right? Or we need to have a different way of thinking or approaching this problem. Okay, and the different way is I'm going to look at this function. I'm going to say that CS becomes maximum as CA approaches 0, right? This is really the only way to do it, because if you do the derivative, you won't be able to solve for a value, because this functional form or this mathematical form diverges at different points. And reaction engineering really, if you become a very technical reactor engineer, it's all maths and differential equations and how to understand Bessel functions and things like that. So this is common. you know, once you get comfortable with this type of stuff, and you have to understand how the different function forms behave and things like that. Anyways, so CS becomes maximum as CA approaches 0. So as CA approaches 0, CS will approach CA node, right? And this is really the maximum value for CS for this type of function. Okay, so this is the way to solve this first one. Again, it's an unconventional problem, but just know it and identify that it really depends on the functional form. Okay, so now let's move on to it. 711, right? It's page 13. So for 711, you're being told to do the same thing. Find the operating condition which maximizes CR in a mixed flow reactor. Okay, so CR in a mixed flow reactor. So again, 7.11, sorry. So I want to maximize CR in a CSTR. So we said in a CSTR, the equation for CR was CR is equal to phi of R over A multiplied by minus delta CA. And we made the determination that this expression is equal to, have a look here. We said this is, CA divided by 5 plus CA multiplied by delta CA or minus delta CA will be CA naught minus CA. CA naught is 40, so I can plug it in directly. So I'm going to get CA over 5 plus CA multiplied by 40 minus CA. And this is the expression I want to maximize. So in order to maximize it, I'm going to take dCr by dCA. And as you can see, this expression, you're going to get a very nice number. It's going to be derivative by dCA of CA into 40 minus CA divided by 5 plus CA, right? And always remember that, you know, U over V, if I want to derive it, I'm going to get U prime V, or, you know, let me clean this up. You're going to get, just remember these simple things, U prime V minus V prime U divided by V squared. And you just remember how to do this. And the expression you're going to get is basically 40 minus 2 CA into CA plus 5 minus 40 CA minus CA squared divided by 5 plus CA squared. If you take this derivative, and I want to solve this for CR equals to 0. Or, you know, I want to solve this for CA basically, so I'm solving this for CA. Do the math, you're going to get CA is equal to 10 moles per meter cubed. Once you have CA, you can get the CR max by basically plugging the CA into this expression, and you're going to get a CR max of 20 moles per meter cubed. Try it, verify these calculations, come back to office hours if you're having a hard time doing it, or send me an email. Okay, let's clear all these drawings. Let's go back to the homework and see what else is left. Okay, so I have 8.1 and 8.2. Okay, let's have a look at 8.1. So 8.1, starting with separate feeds of reactants A and B for the competitive consecutive reactions with stoichiometry and rate as shown below. Sketch the best contacting patterns for both continuous and non-continuous operations to get the desired product. Okay, so this is similar to the first one we did. Let's have a look here. Okay, page 14. Okay, so I have 8.1. My reaction system is, well, let's read this problem again. For continuous and non-continuous operations. Okay, so I have my system. In this case, it's A plus B going to R, and this is the desired product, and it has a reaction rate of R1, and then I have A plus B going to S, or R plus B going to S, sorry, R plus B going to S, and this is undesired, has a reaction rate of R2. And for number one, you're given some information, so you're being told that R1 is equal to K1 CA CB squared, and R2 is equal to K2 CR CB. So I want to maximize R1 compared to R2, right? So if I calculate this ratio, R1 over R2 is equal to K1 over K2, CA CB over CR, right? So in order to maximize this ratio, I want to keep CA and CB to be as high as possible. So in order to do this, I'm going to introduce them both into a PFR at the same time. This way, CA and CB as high as possible. For continuous flow, for an non-continuous flow, so for in a batch reactor, I'm going to again introduce them at the same time, A and B, same time at high concentrations to drive this reaction towards the top or towards R. Okay, and again, we're going to repeat this for all of them. So maybe I'll just do B and then you can do the rest. For B, R1 was K, 1CA CB, R2 was K2 CR CB squared. So if I write the ratio R1 over R2, this will be K1 over K2 CA over CR CB. So in order to maximize this ratio, I want CA to be high and CB to be low. So for a PFR, the way to achieve this, I'm going to introduce A at high concentrations initially, and then I'm going to keep the concentration of B by introducing it at different ports. And for a batch reactor, I'm going to have a tub full of A, or a beaker or a batch reactor full of A, and I'm going to introduce B slowly in a dropwise fashion. This way the concentration of B will be low. And again, you could C and D are the same logic. You can do them at your own time, or you can do them, and submit them with the homework. Okay, so I'm going to stop here. I'm not going to do C and D. I'm going to clear. Let's go back to the homework and let's have a look at the last problems, which is 8.2. Sorry. So for 8.2, you're being told that under appropriate conditions, A decomposes as follows. R is to be produced from 1,000 liters per hour of feed, in which Ca naught is 1 mole per liter, Cr naught is equal to Cs naught equals 0. What size of plug flow reactor will maximize the concentration of R, and what is the concentration in the effluent stream from this reactor? Okay. So in this type of problem, this is 15, this is 8.2. So here I have A going to R going to S. K1 is equal to 0.1, K2 is equal to 0.2, right? And I'm given some other parameters. I'm told V naught is 1,000 liters per hour. Ca naught is 1 mole per liter. And Cr naught is equal to Cs naught equals to 0. And what am I looking for in this problem? Size of plug flow reactor that will maximize the concentration and the concentration on the effluent stream. So I need to find V of the PFR and the tau of the PFR that will maximize concentration of R. That will give me a CR maximum. So in your slides, this week we talked about two equations, right? Or two equations in the quantitative analysis for a PFR and for a CSTR. So in a CSTR, in order to get the maximum of the intermediate, I'm going to use this equation, and to get the maximum time, I'm going to use this equation, right? So I have two equations for a PFR, sorry. This equation on the left, equation to determine the maximum concentration of intermediate in a PFR, and this one on the right, the equation to determine the maximum concentration of PFR. However, in this problem, because K1 and K2 are the same value, so K1 is 0.1 and K2 is 0.1, these equations will fail, okay? So in the case where the K1 and K2 are the same and these equations fail, sorry, you have to use the charts, and your charts are provided in the slides, are also figure 8.3 and Levenspiel. So in this case, I need to look at the line where K1 over K2 is equal to 1. So in this case, I'm looking at this line right here, and the maximum of this line will occur at this point, right, where K1 tau is equal to 1, and C over CA naught is equal to maybe 0.38, and these will be the values. So the CR maximum over CA naught is about 0.38, and this occurs at a K1 tau value of 1. Similarly, you can read this chart to get the conversion, and you have the CR max, you have the conversion. This should be enough for you to determine the volume. So you have the tau, you have the CR max, this should be enough for you to get the volume of the PFR from the performance equation, okay? So this is part A, and you have to remember that the equations fail because K1 is equal to K2, so must use the chart. For number B, I want to do the same thing. However, this is for CSTR. And in this case, the equations will work for a CSTR. So if I go to my slides here and I look at the equations, so for a CSTR, we can calculate it by tau. Calculate the tau is equal to 1 over square root of K1, K2. This is the tau at which I get the maximum concentration of intermediate. And I can use this equation to get the maximum concentration of intermediate. CR max over CA naught is equal to 1 over K2 over K1 to the half plus 1 squared. So let's go to the whiteboard and let's use this. So for a CSTR, the tau, optimum tau, which maximizes my intermediate, is 1 over square root of K1, K2. K1 and K2, they're both 0.1, right? They're both 0.1. K2 is also 0.1 in this case. So 1 over is 10 minutes. And similarly, if I calculate the CR max, the equation is CR max over CA naught is equal to CR max over CA naught is equal to 1 over K2 over K1 to the half plus 1 squared. So it's equal to 1 over square root of K2 over K1 plus 1 squared. Right? Yeah, and this is basically 1. K2 over K1 is 1. 1 to the half is a half plus 1. So it's equal to 1 over square, or 1 over this 2, right? 2 squared is 4. 1 over 4, so CR max is equal to 0.25 moles per meter cubed. Okay, this is the way you use these two equations again, and this will also show up on your test. So you know how to use these equations from the slides. And this is the last problem. The homework, please try it. If you have any problems, having difficulties, come to office hours. It's very important not to fall behind at this stage of the course. Exam 2 will be easy, and then it's going to get hard again towards the end of the semester. Okay, thank you very much. Thank you very much.